All right, how's everyone doing today? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Some people who said they were going to be here last time are not actually here. So my class policies, 15, you're just in time. My class policies call for what? In what circumstances? Less than half the class. So there are 15 people here. There are 45 people remaining in the class. Should we have a quiz? Should we have a quiz? Yes, we will. Okay, so here's what we're going to do. Policy requires a quiz. And here's how we're going to do this, okay? By email. Everybody has a device that's capable of email with them. So prepare an email to clay@cs.georgetown.edu. Give you a second to do this. Y'all ready? Okay, and use the subject line November 22 quiz. Boy, it's almost like I anticipated this would happen. clay@cs.georgetown.edu or clay@georgetown, whichever you prefer. Okay, everybody got that? Subject line, November 22 quiz. That way I'll be able to find it easily. All right, so here we go. What does the following code output? Let me make that a little bigger. Exactly what we talked about the last two classes. If you'd like me to read it over to make sure you can see it clearly, would you like me to do that? Yes? Okay. So here's our, oh man, something went horribly wrong here. There we go. All right, pound include IOStream using namespace standard. Int main, int x equals 12. Int star, what's that mean? Stores the address of an int, address x equals ampersand x. Star addrx, address x equals 7, cout x. What does x output? Just tell me what that program outputs and send it to me. Sure, you can use your notes. That would be fine. Yes, you can. Oh, hurry. We're having a quiz because not half the class is here. So here's what you need to do. You have something that can send email? Do you have something that can send email? Do you have something that can send email? You're too late. We're having a quiz. So, yeah. Come on, man. Get out something that can send email. Seriously, let's go. Hurry. You're holding everyone up. Get out something that can send email. Email to clay@cs.georgetown.edu with the subject November 22 quiz. clay@cs.georgetown.edu, November 22 quiz. And then you have to tell me what this code outputs. Okay? What this code outputs. That's all you have to put in your email is what this code outputs. All right? Yep, the subject line, or the mail at clay@cs.georgetown.edu, November 22 quiz, and the output of this code. Yeah, this one. Okay, so for those of you who are watching online, who are now having this horrible sinking feeling that you have missed a quiz and you're likely to pass or fail the class or something, the quiz is only going to count if you're right on the borderline between like one grade and the other. So this will be like just the little thing that if you're super, super close will push you over. So if you're not here and you're watching this online and you missed the quiz, it probably won't make any difference. But, okay? Everybody got that? All right, so let's go ahead and get started. How are you all doing today? You have a lot you have to make up and talk for the people who aren't here. Okay, Kate, you've never said anything in class. I'm counting on you today. No, it's not. It's fun. I participate every day. I enjoy it. So, right? Okay, so review. We were last time talking about self-referential objects, right? Who wants to tell me what a self-referential object is? Yes, sir. It's an object that has a pointer to another object, typically in its class, right? So it's an object that has a pointer to something else in its class. So what we were talking about last time was the node class, right? And the node class had really two portions of data that it kept track of. One was an integer, right, that represents the data that's stored in the node. And the other is this node star, which means the address of something that's a node called next node. This node star next node is the self-referential portion, right? It's a pointer that points to something else in the same class. Let me ask you a quick question about the node. Here we have an integer for the private data member. Could you have different things in there? Yes, you sure could. Like what? Oh, like a subject, right? You could have a subject, or you could make a subject class that had a pointer to the next subject. And then the data that would be inside that subject would be age, age factor, yada, 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 right? All potentially the same things. So all self-referential classes will have a pointer to something in the class, and it will have some kinds of data. But it doesn't sort of matter what the data is as long as you have this. So we're working with kind of the simplest example we can work with by just making an int. Yeah? Okay, so the question is, when we build, like, this is something that we're going to reference only by address. It won't have a name, so we have to have a pointer to it. So where do we keep this pointer? You need to talk to me after class really fast, okay? So where do we keep this pointer? And the answer is, it can be in main. You can have it inside another class. We'll see. I mean, you can literally put it anywhere. Like anywhere you can put a variable, you can put one of these pointers, okay? For the project, what's going to happen is we are going to have a trial class like we do in project 4. In the trial class, we'll have a pointer that links to the list of subjects, not int main. We'll wrap it in another class, okay? Other questions about this? Everybody good? Okay. So here's pictorially what we were doing, right? We had two private data members, an int and a pointer to a node. So we had that as node star. And what value would an int have, for example? What? No, an int. What would an int have? Like, what would be a typical integer value? It could have 7. It could have any number in there, like 7, right? That would be possible. And then what number would be in this node star area? A hexadecimal number, like what? Wrong. 0x779822OF. But do we ever really care what's in here? Right? We don't. Like, very rarely. Right? Sometimes we do. For debugging, sometimes you want to look at it, but for the most part, we don't really care. All we care about, really, is that this address is pointing at something else. So what I'm going to do in my diagrams, instead of trying to keep track of things by, like, barely human-readable hex addresses, we're just going to use these arrows. Okay? And the arrows will be this. Like, if you have an arrow, it will be a non-null pointer, meaning it is pointing at something that is not 0, which means that the hexadecimal address inside is not 0. It means it's 0x77, 0x2, whatever, like that. And we'll use things like this to represent that. Okay? So if you have an arrow with a point on it, it is a non-null pointer that is pointing off and expects to be pointing at something. Everybody good with that? Silence is assent. You're not good with it then. Okay, we'll have null pointers. What's a null pointer? It points to something. What does it point to? So a null pointer is that hex value inside is actually 0. Okay, so 0 we use as a reference. You can't actually have something at address 0 in box 0 because we're using this as an indicator that the pointer is null. Yep. So it would be, I don't really have a drawing for it, but remember a pointer is it's just like, oh sorry, how do I go back on this? Please go back. It's so hard to go back. So essentially what we're looking at is like here in this one, right? We have two things in here. The top is an integer value, in this case 8, and the bottom is some hexadecimal number. If there is a hexadecimal number in the bottom in that pointer place, and it is not 0, then it expects to be pointing at another node somewhere. But if it is 0, if the value, the hex value is 0, that means it's a null pointer. Okay? And I will draw null pointers like this. Okay? This means it's a null pointer. It's not expecting to point at anything. It's not pointing off into space or anything. Okay? Do you understand the difference between the two? If that address is 0, means it's null, and we'll draw it like this. If it's not 0 and not null, it will be like that, and we expect to see another node at the other end of that arrow. Okay. So, we talked about, briefly we started building a linked list, right? How do we build a linked list? What do we start with? Head, what is head? Pardon? Nope, the head is not the first node. It's a pointer to the first node. And initially, when we're building the list, what is head initialized to? Null, right? So you start with a null pointer. This is the head pointer to your list, and you always want to make sure that you initialize your pointers. You will get into trouble if you do not initialize your pointers. Bad things will happen, okay? Because eventually what will happen is you will declare a pointer, it will have some random number in there, and that random number will not be 0, and you will have a pointer pointing off into memory someplace. And there may not actually be what you're expecting at the other end. There might, instead of a node, be like demons or bad things that will come and set you on fire. Okay? Or at least make your program crash. All right? So initialize your pointers. You always want to start with a null pointer. Then what do we do after that? Yep, you have to add a node, right? And what we've done here is we've changed our head pointer from null to pointing at a new node. How did we get that new node, most likely? From what? The new function, right? If you say new, it will create one of these things. If you say new node, it will create a node. It returns the address, which we store in the head pointer, and then we now have a pointer pointing at it. What is the name of the node that's created? It doesn't have a name. Why not? Because we don't want it to have a name, right? We're trying to get away from having to keep track of individual names. So it doesn't have a name. It has an address. How do we know what its address is again? Because it's stored in this head pointer. Okay? Everybody good? All right. So is a one node linked list particularly useful to us? So what do? We can add another node. We can do this two ways. We can either put a node in the front or put a node in the back. We'll try and look at both today. And if not today, next time, we'll at least do adding to the head of the list. And that way, we can grow out the node. Is 2 nodes enough for us? Nope, so we can add another one. Now we have 3. And if we wanted to look through this list to find things, how would we do it? We would start where? At the head, and we would look at the first node and see if it's what we were looking for. And then how would we find the next node? Find this pointer, go to the next one. How would we get to the third node? Go to the pointer, go to the next one, we're at the last node. How do we know we're at the last node in the list? Because when we look at the pointer, it's null. Okay? So conceptually, that's what's happening. Oddly enough, it is a lot like leading through a vector, isn't it? It's very similar. Uh-huh. Okay, we'll actually talk about how to access the methods in this. Okay? Right now I'm just trying to make sure we all agree on the concept, because once we agree on the concept, we can look at the code. If we start with the code, it's a little bit baffling sometimes, so I just want to make sure everybody's on board with where we're going with this, right? Yeah? No, you can actually add things to the front of the vector. So, but vectors, look, vectors are powerful magic, okay? Vectors use pointers inside, but they have a lot of stuff going on that linked lists don't. Linked lists you can consider kind of like a rudimentary vector. As you go along in a course, like 1 or 2 courses later, you will be well positioned to create things like vectors. Right now, just think that, you know, a vector is a collection of things that you can look through. A linked list is a collection of things you can look through. But a vector has taken a lot of the complexity and hidden it for you, okay, in the class. So they're not exactly the same. Okay, like in a vector, you can jump to like a particular element in the middle. In a linked list, you can't, right? Because you have to go. If I wanted to go to the 100th element, I'd be like first element, second element, third element, fourth element, fifth, sixth, seventh, and have to keep going. And so vectors are a little bit, they're arranged differently than a linked list. Does that make sense? And we'll talk, if we have time on like the last day or 2 of the course, about all the other incredible things you can do with pointers, because there's a lot. Okay. All right, so let's look a little bit more formally. We just talked about how you would look through the list, but let's look a little bit more formally at how would we do that. Okay. So here's what we're going to talk about. We're going to talk about searching the list. All right, going through the list. And since you all asked good questions, we already know this, but searching the list is kind of like the equivalent of looping over a vector, right? So when we go through a vector, how do we look at every element in a vector? With for loop. And what does the for loop look like? Semicolon. Yeah, for an I equals 0, semicolon, I less than or equal to vector dot size, close parentheses, I plus plus. Do your stuff, access square brackets, right? Have you all done this like a billion times now? Right? Okay. So what we're going to show you is the equivalent of doing that with the linked list. Okay? Sort of the equivalent, but looking through the list. So when we do this, we can use it for exactly the same thing that we use when we're looping over vector. We can use it for example, printing out all the elements, right? If you print out all the elements of a linked list, you create that for loop, you go through, you print out each one. You can use it to find a particular element, right? How many of y'all have finished the find subject function of project 4, right? You have that loop, you start looping through. When you find the right position, you return it, okay? Almost exactly the same thing. So what we're going to talk about is the algorithm by which we will do this. And then we will look at the code a little bit later. Okay, everybody good? All right, so here's what we do to loop over a list, okay? The very first thing we do is we create a temporary pointer, okay? And in here I've named it temp. You can name it anything you like. Some people use current, some people use other things. Temp is just a variable name. But the important thing to do initially is to set temp, which is this pointer, to point at the same thing that the head points at. How many pointers do we have pointing at the first node now? How many pointers can we have pointing at a node? As many as you like. There's no limit, right? Because remember, a pointer is just a box holding a memory address, and we can do that as much as we like. Okay? So the very first thing we do is we use a temporary pointer to access the first element that's pointed to by head. And once here, we can do whatever we want. We can check if the value is something we like. We can print the value out, whatever, and we'll see how to do that in just a little bit. But conceptually, the first thing we do is we use a temp pointer, we make it the same as head, and then we look at that first element. Then what do? You do something like temp equals get next node. So it gets this pointer that's pointing at the second element and changes temp to point to the same thing. This is called advancing the pointer. You advance the pointer. Okay? All right, once you've done that, you can access that element again because you have a pointer pointing at it. You can look at the value, you can change the value, you can print out the value, whatever you like. Okay. Then what do we do? Which same thing? Uh-huh. Yep, we change temp to get we get the value out of the node temp is pointing at for the next node, and we change temp to point at that. So now temp is pointing at the last node. We can access the element, we do whatever we like. Now what do we do? What do you mean by keep doing it? How do you know when you're done? Okay, so we do exactly the same thing again. We take temp and we set it to the same, to point at the same thing that the next pointer in the node does. And in this case, what happens is temp ends up being null, right? Because temp was pointing at this last node. When we set temp to be the same as the value inside there, it made temp null. We know we are done, right? You know you're done when temp is null. So you have a while loop, you advance the pointer. When temp is null, you know you're done, and you've looked at every element. Okay? Does that make sense? And we'll write code to do this. Yeah. Temp will be null after it reaches. So our general algorithm is this: you access the element that's pointed to by temp, right? Because you have a pointer to a node, and so you can access the data, do whatever you need to do, and then you set the temp pointer to be whatever the next node was in the node you were pointing at. So when you are pointing at the last node on the list and you advance the pointer, you actually advance it to be null. Uh-huh. Well, that's different. We haven't started talking. This is going across a list that already exists. You will have a list that has some number of boxes in it, but it's like a vector, right? If you have a vector, it has a size. Do you know how many things are in there necessarily? You don't. You can check by using size, so you can loop over it. With the linked list, you can't just use size. There's no easy way to tell how many things are on the list, other than starting at the front and traversing the list. And you know you're done when your temp pointer at the end is null. Okay? The list has a size, but it's not recorded. You would actually have to count it. It would be like you hop on a boat, right, and there's a fishing line that's linked to a bottle in the water. And you know that there's a line that goes to a bottle. How many bottles are underwater? You don't know, right? You got to pull up them and count them. So unless you've kept some sort of separate variable that's counted the number of things you've added to your list, which we have not been doing, then you actually have to traverse the list to find out. Does that make sense? It's not like a vector. Vector is more powerful than magic than we're doing right here. But this is what we're looking at is actually how the magic works. All right, everybody on board so far? All right, we'll take a break in 1 second, but I want to tell you one more thing. How to completely screw this up. Okay? Here is how you really, really, really badly screw up traversing the list. Like not just a little bit badly, but catastrophically badly. Okay? Why am I showing you how to do it wrong? So you don't do it. Okay? This is a super duper common mistake. Incredibly common. So I will show it to you now, and some of you will still do it wrong. It's okay. It happens. But here is how to do it completely wrong. Okay? And the answer is when you traverse the list, use the head pointer instead of creating the temp pointer. All right? Don't create the this is how to do it wrong, so never do this, but here's how you do it wrong. Everybody understand what I'm telling you now is how to do it wrong? I try really hard to avoid that in class because people will just do it wrong and they'll be like, that's what you said in class, but this is how you do it wrong. Okay? You use the head pointer instead of temp. So I'm going to show you pictures of what happens. Notice that at the bottom it says bad, 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 don't do this in red. So what should you never do? Just don't do this, okay? I'm showing you what goes wrong so you can avoid it. This is not what you do. Everybody clear on that? Silence is what, assent in this case? All right, so here's what we do. Instead of using the temp pointer, we use the head pointer. And we access the first element on the list. And then what do? Advance the head pointer. So we move the head pointer from pointing here over to the second node. And now we access the stuff in the node, and we do what we want, and then what do? And then we advance the node, and we advance the pointer, and now we're pointing at the last node, okay? We access the elements in there, right? And then what do? We advance the pointer, and head is now null. And so we know we've reached the end of the list, and everything's fine, right? Because you actually traverse the list. And your program gave you output while you were traversing the list. It said, oh, here's this node, and there's this node, and there's this node. Everything's fine. And then what happens later in your program? Next time you try to access the list, suddenly the list is null. And you're like, what the hell? There was stuff there just a few minutes ago. I'm sorry, minutes? Did I say minutes? I meant microseconds ago, right? There was stuff there a few microseconds ago, and now it's gone because head is null. Where are all your nodes? They're lost in the void. They're there somewhere, but you no longer have a pointer to them, so you cannot get them back. Okay? So in this, if you do it this way, you have lost your list. So what are we not going to do? Don't use the head pointer to traverse the list. Okay, I guarantee you out of this class, probably, even though I've said this, and you're all here and I've emphasized it, at some point on the final exam, 4 or 5 of you will use the head pointer to traverse the list. Okay, and then bad things will happen. Okay, so always use a temporary pointer to always to traverse the list. All right, any questions on conceptually what's going on today? Because we're going to look at those two things. We're going to build a list, and then we are going to traverse the list for printing it out, or for searching it, or for counting how many elements are on it, anything like that. Okay, everybody good? All right, let's take a 1-minute stand-up break in place here. I will go back to what we were doing. So, you missed the quiz at the beginning of the class for low attendance, so afterwards I'll tell you what you need to do. So. What happened? What? That was a hard quiz. That was on topical material. That wasn't a joke. That quiz was on current relevant material to the class. Okay. So, everybody remember being here last class? No? Hey, sit down. Come on, we're classing. All right, so here is our node class that we talked about last time. Just to look at this, it has exactly the same things as last time. It has the 2 private data elements we talked about, an integer and a pointer to the next node. And we have a constructor that just sets things to 0. And that's our default constructor that runs when we call new node. And we have get data, get next node, set data, set next node, yada, yada, yada. Everybody good with that? Do I need to leave that on the screen for right now? Can I have a bunch of money from you? So can I leave this on the screen? Do you need it on the screen, yes or no? Okay, good, thank you. All right, so we have that. And then if we look at main, here's what we worked on. And this was kind of building the list, which we talked about, right? And we can step through this. First of all, we created a pointer to the list. And we did this in int main because we can do it anywhere we want to create a list. And we said node star head equals null, right? This was the first step where we made a pointer and we set it equal to null. Then we created the first node, right? So we have now a list. The list is a head pointer that points at one node. The node currently doesn't have any data inside of it because when we call this constructor, it just called the default constructor and everything is 0. So what we did is we did this. We said, okay, take the head node, right, and dereference it, which means go to the new node that was created, and when you get there, set the data to 4. Now, we noticed when we were compiling that we had to put parentheses around this, right? And I didn't really explain why. Why do you think we have to put parentheses around that? Yep. Exactly. So this can be, if we don't have the parentheses, then we have a problem, right? Does this mean dereference head set data for, which might return an address? Or does it mean first dereference the head and that set data? So the compiler complained that we had to, it was ambiguous as to what we meant, so we had to put parentheses around it. Okay. Does that make sense? Because that makes sure the order of operations happens in the correct way, that we end up with a node, because star head means dereference head, which gives us a node, and then we called set data on the node. Okay. What I didn't tell you was this. Programmers are what? How easy is it to type parentheses all the time? All right, we're lazy. So this actually is a little bit hard to read as part of it. So for this dereferencing a object and calling a method, there is a special notation for it, okay? And it looks like this. Head, arrow, set data. These two things are equivalent, okay? This little arrow operator, which is a dash and then a comparison. I don't remember if this is greater than sign. Is that greater than? All right, dash greater than means dereference the head pointer, and when you get there, call the set data method. So it is exactly the same as open parentheses, star head, close parentheses, dot set data. And it is much more common for people to use this arrow notation than it is for other things. Okay? Everybody good with that? Okay. All right, so what I'm going to do is I'll comment this out. And you know what I'm going to do? I'm going to change all of these to use the same notation, because that is the notation we'll be using from here on out. Like that. Okay. So using this arrow notation, we create a new node. Well, I'm sorry, we create a pointer with its null. We create a new node that's 0. We say head, follow the pointer, and when you get there, set the data to 4. We make a temporary pointer. Yes, sir. Okay. Think of it this way, right? We are standing on our fishing boat. We have a string. You want to drink the water. There's a bottle tied to your string. You want to drink the water in the bottle. What do you have to do? You got to pull on the string to get the bottle first. So the pointer is just like the string, right? And so you have to dereference the string to get to the object. You have to dereference the pointer to get to the object, and you can only do operations on the object. Does that sort of make sense? Yeah, so it's like if you to use the child holding hands, right? Like before you gave the child candy or something like that, you would have to pull on the child's hand to get them close enough. All right, I like the string one a little bit better for this one. So anyway, so I've been doing this for years, and I'm still trying to come up with a good analogy. The string on the fishing boat is the best one. We should have an analogy competition someday, maybe on the final exam. So, okay. So, everybody with me on this, right? We made a new node, we set the data to 4. Now we made a temporary pointer. And the temporary pointer is going to be to hold this other node. And we can go back to our picture we had here, if I get it right. So we created a temporary pointer that points to a new node. We sent the data in the new node to 11, and then we set temp next node head, and head equals temp. So here's essentially what we did. I lost my picture. Here we go. Here's essentially what we did, right? We created this new node 11. We had it point at the first node, and then we moved head to point at the same node. Okay? I went through that kind of quickly. But look at it this way. We're standing on our boat. We have a string with one bottle in the water, and we want to put a second bottle in the water. Everybody with me, analogy-wise? We can do one of two things. We can either take the string off the boat, tie it to the new bottle, and then throw both in, as long as we're holding onto a string on that. Or we can pull all the bottles up and tie the string to the end. Which is easier? Putting it on the front is easier, right? You untie the string from the boat, tie it on the bottle, tie the string from the bottle to the boat. Your string of bottles is longer, but you haven't lost anything. If you want to add it to the end, you have to like haul everything up, find the end, and then tie it on the end, and then put everything back in the water. Okay? You're getting ahead of yourself. Okay? You're getting ahead of yourself. So let's look at smaller pieces before we get to that. Okay. So everybody, does this make sense to everybody? Hands up if it makes sense. Hands up if it doesn't sort of make sense. Okay, what is confusing? Okay. Okay, we'll do some more examples as we go along, and maybe that'll help. Okay. All right, so let me ask you a question. Is adding something to the list something that we will do frequently, do you believe? How many of you think we will frequently add something to the list? How many of you think we will never add things to the list? Except maybe this one time, and you're hoping it'll go away after this. How many of you have no opinion on the subject? Okay. We are going to frequently add things to the list. If you're going to do things frequently when you're programming, what do you do? Make a function. Ooh, that's a good idea. How would you all like to make a function that does something, that adds something to the head of the list? Yes? How many of you are just ready to leave? Okay. So let's do this. What we're going to do is I am going to kind of create a function that adds things to the list. Okay. Now, we have our choice. We could either create a new class, or we could just do it as a function. Which one do you want to do? Bad choice. Let's do it as a class. So we're going to have a node class, but a node is just one element in what? So we can have a linked list class as well. Okay. If we have a linked list class, we have to have some private data for it. What do you think the private data is going to be? What do you actually have to keep track of at all times in a linked list? The head pointer. If you lose your head pointer, you're in bad trouble. Okay? So what we're going to do is we're going to create a linked list, and this linked list is going to have a pointer to a node that is the head of the list. Everybody good with that? So our class, this linked list, we know we have a pointer to the linked list. Okay. We know we have to have a constructor for this, right? What does our constructor have to do? Actually, let me make linked list capitalized because, I don't know. Typically, we make our classes capitalized, and I haven't been doing that. So, all right. What do we have to initialize in the constructor? Why do we have to make the head pointer null? Why are we going to make our head pointer null? Because if we don't pain and terror will follow, okay? It will be bad for you if you don't. You always initialize your pointers. When we create a new linked list, the only thing that's really inside it is this pointer. We have to make sure it's initialized. How do we initialize this? Okay, so head equals null. Okay. Now, we might want to do some operation. Yeah. Oh, yes, thank you. I forgot the public keyword. Thank you very much. Sorry, I'm out of candy for the semester. So. Okay. What, I mean, you think I'm going to buy another 5-pound bag of candy just for like 4 more classes? I'll tell you what, if you all are really good, I'll bring you some of my kids' leftover Halloween candy. The problem is it comes in like packages that are really hard to throw. Like I select my candy for throwability, and the stuff that they have from Halloween is like, some of it's like in paper wrappers, and I don't know. I'm worried about your all physical safety with that candy. So, okay, so we have a linked list. The linked list is going to have a pointer to the head of the list. The list itself is going to be composed of what? The linked list is going to be composed of nodes, right? And we have a pointer to the first node, and all the other things will be nodes. Everybody sort of with me on this? Okay. So instead of handling our pointers in main, okay, what might we want to do to our linked list? We might want to add an element to our list, okay? And what we're going to do in this adding our element is we're actually going to get the integer that we use to create the node. Okay, so we will get an integer value, and then we will use it to create the, so I'm going to split the screen a little bit here so we can kind of keep the class definition in sight while we do some of the methods. Okay. And we're going to rewrite main, so in fact, I'm just going to delete all this stuff. I thought I was going to delete all this stuff. All right. So now we want to add something to the, we add an element to the linked list. So we create the linked list method. Oh, this is going to, what is it going to return? It's going to be void. We don't need any return, void linked list, : add element, int x, where x is going to be the thing that is being added. Okay, so how do we add an element to the list? Create temp what? Create a temp pointer that points at a node, temp. And then what do we set that to? Nope. We can start by setting it to null. It is always safe to set things to null, so I like that. Now, we have a temporary pointer. It's not pointing at anything. We want it to point at something. What is it we want it to point at? A new node, right? So we say temp equals new node. So now temp is pointing at a new node. What values are inside that node? And what do we set in the constructor of the node class? Let's go back and look, right? So in our constructor in the node class, when we create a new node, we set data equal to 0 and next node equal to null. So what is the data over here when we create a new node that is pointed at by temp? 0. And what is the pointer in the node that is pointing at by temp point to? Null, right? When we create a new node, it calls this default constructor, so data is 0, and the next node is null. So temp is now a pointer that points at an empty node. Everybody with me? Okay. So now we have to change the node, the value of the node, though, don't we? What do we have to change it to? No, not whatever we want. We've been told. What do we have to change it to? We want to change the value of the node to be this parameter, which is x. So x gets the value copied in. We want to change it. How do we change the value of the node? Temp, yeah, arrow. Uh-huh. Perfect. Oh, thank you. She was perfect. My typing was imperfect. So, all right. So, new node temp is null. We have a pointer that points at nothing. Temp equals new node. We create a new node that has no value. Temp arrow means follow the pointer, the temp, and when you get to the node at the end, call the setData method and change it to x. X was this parameter that came in, so that will be set to whatever. Okay, now what do we have to do? Okay. Now what we want is we want to have head pointing at our list, right? Is head pointing at this node? Is anything on the list pointing at this node? It's not, right? This node exists entirely separately from the list. So what we have to do now is somehow link that node into the list. Okay? So how do we add that node into the list? Okay, so we might be able to do this, temp equals head. But you know what just happened? We lost our new node. What we had was this. I'm going to draw some pictures that won't make it on the screen. We have temp pointer. It points at our node, which points at nothing, and we set this to x. Whatever's in here is x. And we had a separate head pointer over here that pointed off at something. If you do temp equals head, you've lost your new node because you changed temp to point at whatever head is pointing at. Head may or may not be null. Does that make sense? So temp equals head doesn't quite do it. What we want is we want to link this thing into the list by changing this pointer right here. Right? Here's temp. It points at our node. We have a pointer in this node, and we want it to link it to the list. How do we link this pointer into the list? Pardon? I think at least two people said it, but they talked over each other. Yeah. Exactly. Temp, arrow, set, next, node, head. So now what we have is we have a pointer to temp, and we have this pointer pointing over to whatever head points at. Now head could be pointing at something, it could be null, right? Doesn't really matter. And then what do we have to do now? So temp is pointing at the first item on the list, but now head is now pointing at the second item on the list, probably. Head equals temp, and we just link it right in. That's it. We've added something to our list right there. Ah. All right. Is this clear to everybody? And I fully expect the answer to be no. So is this clear to everybody? If this is clear to you, raise your hand. If it is not clear, raise your hand. Perfect. Great. Here's what we're going to do. We're going to go draw a picture. Okay? Because pictures are helpful, aren't they? Okay. So first thing we do, let's put the code on the screen. Whoops. All right, let's see if that is good enough to read. How's that? Is that good enough to read? I'll even take the comments out, and that'll take up a little space, okay? And what we can do is we can go through this and actually kind of stop motion, animate what's happening. Okay. Everybody with me on this so far? All right, so where do we start this code? And here we start void link list index. So what's the first thing that we do? Create a temporary node, a pointer to a node. Uh-oh, I lost some of my pieces here. Okay, so here's what we do. We create a new thing called temp. Right? And temp is initially null, just like that. In fact, you know what we're going to do? Let's do this. Let's make it even better. We will number each step. 1, 2, 3, 4, and 5. Okay, so over here, this is step 1. Temp, we create a pointer and it's null. Everybody with me on this step? Is this going to be easier to understand, do you think? Okay, because pictures help. So, all right, that's step 1. Step 2, temp equals new node. What happens? Yep, we get a new box. And this new box appears right here, and initially has, initially its pointer is null. What value does it have inside here? 0. And temp is no longer a null node. It is now, I've lost all my pointers. Oh no. And temp is now a pointer that points at this. Okay? Ah, wait. You know what? I totally screwed up. I meant to number this too. All right, hang on. Okay. Step 1, all we had was a null node. There we go. Step 2, we had temp, but temp was pointing at a new node, which is right here. And this thing had that. That was step 2. How's that? Is that better? Okay. So step 1, temp equals node, temp equals new node. Step 3, temp set data x. And why don't we just make this a real number? We can just make it x. Doesn't matter. What happens in step 3? Yep, in step 3, the 0 becomes x. I'm going to run out of space here, sorry. Okay. All right. Step 4, what happens? I've lost temp. This is very confusing. This isn't working as well as I might like. Sorry about that. I normally draw this on the chalkboard, but I don't want people to be able to see it on the video, so this is a little bit awkward, but maybe better than the chalkboard. So step 3. Step 3 is there. Oh man. Experiments in teaching pointers. Failed experiments in teaching pointers? What do you think? All right, well, there we go. Step 1, 2, 3. There is temp pointing at x, okay? Now what happens? The 4th step, okay? We haven't talked about it before, but we have some pointer named head, and we have head down here, and head is pointing off somewhere. We don't actually know or care if head is null or if it points at something. Right? We don't care. What we care about is that in this step 4, that this pointer right here points at the same thing. So if head is pointing over there, temp is also pointing to where head is. It may be null or it may be another node, right? Because if it's null the first time, if this is the first time we're adding something to the list, it'll be null. If it's not the first time on the list, it will be pointing at some other nodes that point at other things. Okay? All right. So this is step 4. Okay, step 4. And then step 5, what happens? Head equals temp. So now what we do in step 5 is, sorry, I should have done something better with this. Head equals temp, so head points over here, and this is step 5. And we'll try to move this someplace where it won't move other random things around too. Okay. So now the head of the list is pointing at the first element. This thing is pointing off, hopefully, at the second element, or whatever. And so we have linked head into the front of the list. All right. Does that make sense?
So the thing that the head was pointing before,
Uh-huh. Because this pointer inside the node is now pointing at whatever head was pointing at before. Okay. All right, who have I baffled by this horrible artwork? I baffled you? Yeah, I'm sorry. Let's do it quickly on the chalkboard, okay? So if you missed class today, too bad for you, but let's go through step 1, okay? Step 1, and I'll go back to the actual code so we can see. Step 1 is we created the pointer. So initially we had a thing called head, right? And that's just part of the class. Do you want this to be null or do you want it to be pointing at something? How many of you all say null? How many say pointing at something? Okay. It starts off as null. This is the first time we're adding something to the list. So step 1 is we create this temp pointer. And what is it pointing at? Null. Okay. Step 2, we do what? We create a node, and this points at this node. What values does this node have? 0, and what's it pointer pointing at? Null. Okay. Step 3, what do we do? Yep, we have temp. We change the value in our node to whatever it wants to be. This thing still points at null. With me so far? Step 4, now we actually have to link this into the list. So what we have to do is we have to make it so that temp, whatever the pointer in the node that temp points at the same thing head does. In this case, head is null, right? So our picture actually doesn't really change. And head is null. And then in step 5, head changes to point at this as well. So now we have a linked list because head points at the first item points at the second item. It's just that there is no second item. Okay. Everybody with me on this? Sorry with the drawing on the picture thing. It doesn't really work that well as much as I'd hoped. It's better than me trying to type pictures though, isn't it? Marginally. So. All right, let's take a 1-minute break, stretch. Let me see if I can make this a little bit clearer. Okay, so I'll put this picture online too, and you can sort of look at it. So, okay. All right. Yes? Are you just saying hi or you have a question? Uh-huh. Uh-huh. Nope. There's only one pointer that's called temp. The pointer that's called temp points to this node. This pointer doesn't have a name because it's part of this node that doesn't have a name. But we can find out what it is by doing temp arrow, which means go to this node, and then saying get next node. It will tell us what that is. Okay, so it doesn't. So it has. It literally. It has a name. It's called next node, and it's next node of this node that doesn't have a name. There are no names. So to get there, you have to go temp, get next node, or set next node.
Why is it that we have to create, and try to link this all together instead of just like how we do it in vectors, just push things in?
Why can't we just push things in like vectors? What do you think is going on inside the vector? This is what's going on inside the vector. Some version of this. So, why do we have to do things manually when the vector will do it for us? Is that what you're asking? Because we're programmers and we're lazy? Because we want to know what's going on. And because this whole introduction into pointers and what pointers are doing is just barely scratching the surface of what pointers can do. Remember day one, I told you this class shouldn't be named Computer Science 1. It should be named something else. What was that? Do you remember? That day was crazy, right? That was like 4 years ago. It feels we've learned so much. Day one, I said Computer Science 1 shouldn't be called Computer Science 1. It should be called Power through Computer Science 1. The power you're going to get over the computer is going to come through pointers. Pointers are power. This is the simplest example of pointers we can possibly do. I don't even want to guess what the most complicated example we could do would be. Okay? But I will show you some other examples a little bit later in the semester, just to give you a preview of coming attractions for other classes should you decide to take more. Okay? Like, if our society is capitalism, this is the introduction to money. Okay? Seriously, right? What drives things in the capitalistic society? Capital, money. In computers, pointers are power. This is like your introduction to money. And you're like, why are we using money? Because I used to be able to just swap my cupcake for like a soda, and now we have this other thing in between that's confusing me. This is power, man. Money is power. Pointers are power. Okay? Oh yeah. Oh yeah. So are pointers a thing across languages? The answer is yes and no. All languages use pointers. Not all languages make pointers available to the programmer. So Java, how many of you have programmed in Java? How many use pointers in Java? Because Java is nerf C++, and they have made it nerf and soft and cushy so you don't hurt yourself by taking away the pointers. Now, nothing wrong with nerf languages because it's easy to screw up with pointers. If you do something wrong with pointers, the results are relatively horrible on occasion. So Java keeps you from making those bad mistakes, but Java is doing pointers in the background. It's just not showing it to you. Okay? Python as well. Python might have pointers. I'm not sure, but they don't really use it that way. So. All right. Everybody still on board? So we have this method that will, in our list, that will add something to the head of the list. So we believe. How do we actually know if that thing works or not? See out what? So if we see out where the head is pointing, and here let's just do this. Let's go ahead and create a linked list in main. Because we haven't actually compiled this to make sure it works. So we make the list. Let's actually just see if this works or not. Ooh, that was nice. Okay, and if we run this, it runs beautifully, perfectly, no problems. So everything's fine, right? But we haven't actually done anything other than create the list. So what we really want to do is do list, add element, What number would you like to add to the list? 666. So we can compile that, and we can run it. It seemed to work, but how do we know? See out. What are we going to see out? All right, here's what we need. What we really need to do is we really need something like this. What we need is something in the class that will print out the list. How about that? How about that, void print list? Does that work? Okay, so let's write that, void, I belong to the linked list class, and my name is print list, and I take no parameters, and I don't return anything. All I do is traverse the list and print things out. Okay, do you remember we talked earlier in the class about how to traverse the list? How do we traverse the list? By using a temp. So let's just go back and look at that really fast. Right? Here's what we're going to do. We're going to use temp, and temp's going to access the list, then move, then access, then move, then access, then move. And when it gets to null, we know we're done. That's our algorithm. So let's do this. Wait, where's my... All right, so we need a temp pointer. And what type is temp going to be? A node? Does that seem right? Star. It's the address of a node. It's a pointer. And what do we initialize this to be? We can do null if you want. But where are we going to do? What are we actually going to do with temp? We're going to set it equal to something, not the next node, not null. Eventually get next node. Initially, we're going to set it equal to head. Okay? So what we're doing is we say this thing is equal to the head of the list. And if we go back to our little thing right here, right? Initially, this pointer right here is head. Temp points at the same thing as head. To make temp point to the same thing as head, you just say temp equals head. So we do temp equals head. Yep. Nope, because it's in a different method, right? And it has scope only within that method. Okay, we're going to revisit scope one more time before the end of the semester. All right, so temp equals head. All right, so we have a loop, and here's what our loop does. While temp isn't equal to null, and you're going to see this loop an awful lot, because this is what we were talking about is kind of the equivalent of the for loop in a vector. While temp is not equal to null, what we want to do in this case is cout temp get data. So we output the thing, we access the element, and if we go back here, right, the first thing we do is we use a temporary pointer to access the element, and that's what we're doing by doing temp get data. Everybody with me? So now that we've accessed the element, what do? We what? We advance the pointer. So we advance the pointer. So we change temp to point at the same thing the pointer in the node points to. Okay? And the way we do that is we say temp equals temp arrow get next node. So set the pointer equal to head. If temp is not null, that means if we actually have something on the list, we print out the data, and then we move the pointer to point at the next node. That's it. That's everything. So let's go down here into our main again and do list.print list. See if that compiles. It does. When we run, we see we have 666. Okay. We go over this list, this kind of thing more than this. We're going to go over it again. But just to look at it, what we do, this is how we traverse the list, just like we loop over a vector. We say temp star equals head, which means we set this temporary vector to point to the first thing on the list. We access the element on the list that we're interested in. We do whatever we want with this node, which in the print case is just get data and cout it. Then we change the pointer to point at the node on the list. And the way we do that is temp equals temp arrow get next node. Because what that means is temp, we have it this, right? Temp arrow means go to this node. Get next node gets this pointer that's pointing over there. And then temp equals changes temp to point at the same thing. All right, who's with me? Who's against me? Thank you for showing up. So let's add some other stuff to the list and see what happens. Anybody have other? Any other numbers? I can't imagine why that number is important. What else? What else? No. Yes, we probably could do 2 minus 8 here. I take that back. We could do 2 minus 8 here. Sorry. Because it'll do the math before it does it. So, all right. So when we print this list, what is going to print out? The list of numbers in the order that they were put in there. 6, 6, 6, 5, 4, 9, 7, 0, minus 6. Opposite. Why opposite? Because every time you put a new one on, you add it to the front, and it pushes the others down. So I would expect to see these in reverse order. So if we run this, I expect to see minus 607, 549, 666. Minus 607. All right. Any questions about this? Yes, you're going to have to load the file. It's okay. I've taught you everything you need. Read something out of the file, and then do list.addElement with whatever you want. You have almost what... It doesn't matter what order it's in, right? In this case, it doesn't matter what order it's in. And we'll talk about... the project is actually posted right now, if you want to look at it over Thanksgiving. I think I forgot to link it from my webpage, but I'll do that when I get back to my office. But you can look at it and see if you like. So, almost everything. You have a good base on it. At least we've talked about it in class. I do not assume that you know things just because I talked about it once. How's that? I believe you have an introduction to it, so you can go do it yourself and then know it when you're done. How's that? All right. Have a good Thanksgiving.